Dear students, in the previous lecture I have discussed about scheduling a project where it has uncertain activity durations. In this lecture I am going to discuss about time cost trade off. So, the agenda for this lecture is time cost trade off and crashing activity times, and very important thing is how to use linear programming for crashing a project network. What is this time cost trade off? When determining the time estimates for an activities in a project, the project manager bases these estimates on the number of resources that will be assigned to an activity. What are the resources? Resources like workers, equipment, supplies availability and so on. The original developers of CPM provides the project manager with the option of adding resources to selected activities to reduce the project completion time. Suppose I have a project, it has say it is taking this many days, for example 6. Okay. So, what will happen when you add more resources? So, what will, there is a possibility I can reduce this project this activity by say from 6 to 5. So, what we can do when you supply more resources, the activity duration can be minimized. The added resources generally increase the project cost. So, when we add more resources, the project cost increases. So, the decision to reduce activity time must take into consideration the additional cost involved. In effect, the project manager must make a decision that involves trading additional project cost versus reduced activity times. So, what will happen? We need to have a trade off between cost and time. What will happen? When you compress the time, the cost will increase. Instead of finishing this activity for 6 days, by supplying more resources, if you are planning to reduce within 5 days, the time will decrease, but the cost of finishing this activity within 5 days will increase. So, the project managers need to understand the trade off between cost and time. So, in this lecture we are going to discuss about this cost versus time. So, what we are going to do in this lecture? What is the optimal project completion time so that the cost can be minimized? That is the objective of this lecture. Now, I am going to explain this time cost trade off with the help of a problem. This problem, the reference for this problem is the book Anderson et al. What is this problem says? There is a two machine maintenance project consisting of 5 activities. Okay. They want to do maintenance for 2 machines. For that there are 5 activities. Management has substantial experience with similar projects, and the times for maintenance activities have very little variability. Hence, a single time estimate is given for each activity. So, activity A, B, C, D, E, there is a predecessor for each activity is given, and the expected time. When you look at this expected time, for example, for completing activity A, it will take only 7 days. Since the maintenance activity is a repetitive in nature, based on their experience, they are able to provide a single time estimate. That is why it is exactly 7 days. What is the first task? The first task is we have to draw the project network, then we have to find out the how much time it is going to take for completing all the 5 activities. So, what I have done? I have drawn this network. Now, I am going to find out how much time it is going to take. So, I am going to use the same notation which we have followed in the previous class, that is See, for example, here activity name, activity duration. Here it will be earliest starting time, here it will be earliest finishing time, here latest starting time, here latest finishing time. Okay. So, first I am going to use forward pass. Okay. What is this forward pass? So, for activity A there is no precedence. So, it can start on 0th day, that will be earliest starting time. What will be earliest finishing time? Duration is 7. So, 0 plus 7 it is 7. Similarly, for activity C there is no predecessor. So, it can start on 0th day, it will finish 0 plus 6 6th day. For activity B it will start on 7th day. You see that the time I am writing in a cumulative scale. So, why I have written 7th day? Because the earliest finishing time of previous activity is 7 days. Only the activity B can be started only after 7th day. So, 7 plus 3 equal to 10th. So, here see activity C will be completed only on 6th day. So, activity D can be started only after 6th day. So, the duration of activities 3 is 9. So, it is 9. Now, we have to find out the earliest starting time for activity E. What happened? You see there is a 10, there is a 9. So, as per the forward pass algorithm, we have to consider the largest value of earliest starting time. What is the largest value? 10. Between the 10 is the largest value between 10 and 9. So, 10 plus 2 is 12. So, it will take 12 days to complete the whole project. Now, I am going to discuss about this backward pass. So, 12 is your latest finishing time. If the 12 is the latest finishing time, what will be the latest starting time? So, 12 minus 2, 10. Okay. Now, for activity D, the latest finishing time is 10, because the latest starting time of activity E is 10, that will be equal to latest finishing time of activity D, that is the preceding activity. So, 10 minus 3 is 7. Okay. Now, this is 7, 7 minus 6 is 1. For activity B, the latest finishing time is 10. So, 10 minus 7 is 3, 10 minus 3 is 7. So, it is 7, 7 minus 7 it is 0. How to find out the critical path? The path which is taking longest duration. Otherwise, if you connect all critical activities, what is the critical activities? Activities which are having 0 float or 0 slack. So, what is the slack? We have discussed in the previous class. The slack is the difference between latest starting time minus earliest starting time. That means the difference between this value and this value. So, it is 0. So, here 7 minus 0, 0, 0 minus 0. So, there are 3 critical activities, activity A, B, E. So, this path, which one? This path A, B, B, E. So, the path A, B, E is your critical path. What is the project duration? 12 days. Making the forward pass and backward pass, calculation for the network in the figure which I have shown in the previous slide, we obtained the activity schedule shown in table 2 like this. We found the earliest starting time for each activity and latest starting time and earliest finishing time and latest finishing time. We got the slack, wherever slack is 0, that path is a critical path. Then the 0 slack times and thus the critical path are associated with activities is ABE. So, the length of the critical path and thus the total time required to complete the project is 12 days, which I have shown you in the previous slide. Now, we are going to discuss the concept of crashing. Now, suppose the current production level makes completing the maintenance project within 10 days, we have to finish. Within 10 days, we have to finish the maintenance activities. It will take 12 days, but the management decided to finish this maintenance activity within 10 days. So, when you reduce 12 days to 10 days, time will be decreased, but there will be an increase in cost. That is what we are going to do. By looking at the length of the critical path of the network 12 days, we realize the meeting the desired project completion time is impossible unless we can shorten selected activity times. Only possibility to reduce the project duration to 10 days is for some of the activities we have to compress the time. So, this shortening of activity times, which usually can be achieved by adding additional resources, is referred to as crashing. Because the added resources associated with the crashing activity times usually result in added project cost. We will want to identify the activities that cost least to crash and then crash those activities by only the amount necessary to meet the desired project completion time. So, there will be different activities. So, what we have to do? We have to crash or we have to reduce the time of activity which takes the minimum cost. That is the logic here, and there will be a limitation. So, for each activity only this much amount can be crashed, this much duration can be crashed. That constraint also need to be considered. So, to determine where and how much to crash activity times, we need information on how much activity can be crashed and how much crashing process cost. So, we need to have the time and the cost. Hence, we must ask the following information. First information is activity cost under normal or expected activity time. Second one, the time to complete the activity under maximum crashing, that is the shortest possible activity time, and activity cost under maximum crashing. So, this information is required for completing the crashing activity. Now, I am going to explain the maximum possible reduction in time for activity I. Let Ti is equal to expected time for an activity. For example, I have an activity like this, say it is taking 10 days. Okay. So, the Ti is nothing but this 10, expected time for activity I. Ti dash, time for an activity I under maximum crashing. For example, I can crash up to say 6 days. So, the maximum possible reduction in time for an activity I due to crashing is, so what I can write, Mi is nothing but this 10 minus 6. So, Ti minus Ti dash. Let Ci denote the cost of activity under normal time. Ci dash denotes the cost of activity under maximum crashing. Thus, per unit time, that is the crashing cost Ki for each activity is Ki equal to Ci dash minus Ci upon Mi. For example, if the normal or expected time for activity A is 7 days, for example, say this is 7 days, okay, and the cost of Ca is $500 and The time under maximum crashing is 4 days and the cost of crashing it to 4 days is $800. So, from the equation 1 and 2, so this is equation 2, the maximum possible reduction in time for activity A is 7 minus 3 days. So, there is an activity like this. So, normally we can finish on 7 days, the cost for this is $500. If you compress this into 4 days, the cost is $800. So, first I am finding how much time we can crash it, that is 7 minus 4 is 3, and I am going to find out per day crashing time. So, with the crashing cost of Ka, we got the Ka represents per day crashing cost. So, the difference in cost is 800 minus 500. You see this 800, difference in cost is 800 minus 500, the difference in time is 3, 7 minus 4 3. So, when you simplify this, so 300 upon 3, this is 100. So, this 100 represents per day crashing cost. Okay. So, this $100 represents crashing cost per day. We make the assumption that any portion or fraction of activity crash time can be achieved by corresponding portion of activity crashing cost. So, what is the meaning that if you are crashing, that means if you are compressing the time, that is achievable by adding the additional cost, that is the crashing cost. For example, if we decided to crash activity A by only 1.5 days, the added cost would be 1.5 multiplied by 100, $150 only for crashing cost. Apart from this, so there is a $500 for normal cost. So, the total cost would be 500 plus 150 equal to $650. Now, in this table, for each activity, the normal time and crash time is given and the normal cost and crashing cost is given. For example, for activity C, it can be normally completed within 6 days. The cost for finishing this 6 days is $500. If you compress from 6 days to 4 days, the crashing cost is say $900. So, now how many days we can crash? 6 minus 4, 2 days we can crash it. What is the per day crashing cost? So, what is the difference in cost? 900 minus 500 is a 400, 400 divided by 2 it is 200. So, $200 is per day crashing cost. That means, you see that if it is 6 days, if you are making it to 5 days, there will be $200 will be extra. So, 500 plus 200, 700. Like this, for each activity there is a per day crashing cost is found. Then apart from this, there is a total cost $1,700. This figure shows the graph of the time cost relationship for activity A. For activity A, the normal duration is 7 days, that is a normal operation. The cost for completing this activity for 7 days is $500. When you decrease this cost, when you compress this, not cost, the time, for example 4 days, the cost will be $800. So, what we are understanding, when you compress the time, the cost is increasing. The complete normal and crash activity data for the 2 machine maintenance project are given in the previous slide that I have shown you. Which activity should be crashed and how much? to meet the 10-day project completion deadline at minimum cost. Because the management is expecting the maintenance activity need to be done within 10 days, but actually it is taking 12 days. So, what will be your first reaction to this question? Maybe to consider crashing critical activities. What are the critical activities? A, B, E. Because if you reduce only on critical activity, the project duration can be compressed. If you do the crashing for non-critical activity, that is not required, because that will not affect your total project completion time. Activity A has the lowest crashing cost per day of 3. You see this activity A, right, the lowest, because the critical activities are A, B, E. Okay. So, corresponding cost is 100, 150, 250. The lowest crashing cost per day is 100 rupees, that is for activity A. So, what we can do, the activity A we can maximum crash for 3 days. Okay. Now, what we can do, we can crash it for 2 days, so that the project can be completed within 10 days instead of 12 days. Keep in mind, however, that as you crash the current critical activities, the other path may become critical. So, what will happen when you crash this, the another path which are non-critical also may become critical path. Thus, you will need to check the critical path in the revised network and perhaps either identify the additional activities to crash or modify your initial crashing decision. For a small network, this trial and error approach can be used to make crashing decisions. But in larger network, however, a mathematical procedure is required to determine the optimal crashing decisions. This mathematical procedures I am going to explain. This mathematical procedure is nothing but your linear programming. So, what I am going to do now, with the help of linear programming, I am going to do this crashing activity. So, the method is called linear programming model for crashing. Let us describe how linear programming can be used to solve the network crashing problem. With PERT and CPM, we know that when activity starts at its earliest starting time, so the finishing time will be the earliest starting time plus activity time. Okay. You might remember like this. Can you recollect? This is A, for example, what is the duration for this? I think 7. So, what will happen? This finishing time. So, here, so the finishing time will be the earliest starting time is 0. So, 0 plus 7. So, that will be your earliest finishing time. However, if slack time is associated with an activity, what is the slack time? Sometime instead of starting at the 0th day, we can start on the first day or second day if there is a slack is available. Okay. If the slack time is associated with activity, then the activity need not start at its earliest start time. So, what we can do in this case, we may have the finish time will be greater than earliest starting time plus activity time. Because we do not know ahead of time whether an activity will start at its earliest start time, we use the following inequality to show the general relationship among finish time, earliest start time and activity time for each activity. What is that the general relationship? The finishing time is greater than or equal to earliest starting time plus activity time, activity duration time. Consider an activity A which has expected time of 7 days. Let XA is equal to finishing time for an activity A. Then YA is amount of time activity A is crashed. If we assume that a project begins at 0, the earliest start time for activity A is 0. So, I am writing like this. So, the earliest starting time is 0, because the time for activity A is reduced by amount of time that activity A is crashed. The finish time for activity A must satisfy the following relationship. What is that? This XA greater than or equal to 0 plus 7 minus YA. So, what is the 7? It is the duration. What is YA? The YA is how much time we are going to crash it. So, XA, this point is nothing but earliest finishing time. XA should be earliest starting time 0 plus 7, that is duration, minus how much time we are going to crash it. So, when you bring this YA on the left hand side, it will become XA plus YA is greater than 7. If we follow the same approach that we used for activity A, the constraint corresponding to the finish time for activity C. What is that activity C? Activity C is like this. Activity Z, the duration is 6 days, the earliest starting time is 0, then it is 6 minus YC. Okay. So, what will happen? This XC will be greater than or equal to 0 plus 6 minus YC. What is the 6? The 6 is the project duration. What is 0? Earliest starting time. What is YC? How much time we can crash. See, Y is the amount of time that activity I is crashed. Like this, we can write the equation for all the activities. That is what I am going to do in the next slide. So, what I am going to do? I am going to write the equations for all the activities. For example, here it is 0. So, how I can write it? So, XA is greater than or equal to 0 plus 7 minus YA. For activity B, the XB earliest finishing time will be greater than. Now, you see this here the earliest starting time will be XA. For activity B, the earliest starting time will be XA. So, XA plus 3 minus YB. Now, we come to activity C. So, here it is 0. So, XC is greater than or equal to 0 plus 6 minus YC. Now, for activity D, so XD I am writing here, XD is greater than or equal to XC plus 3 minus YD. What is the YD? How much time this activity D can be crashed. Now, we have to write for activity E. So, generally what we used to do, the largest value of the latest finish time will be the earliest starting time. So, we are going to write it for both the activities, because we do not know which is the largest one. So, there will be two equations for this. What is the two equation? So, XE will be greater than or equal to the earliest starting time, it may be XB plus 2 minus YE, that is one possibility. Otherwise, the XE is greater than or equal to the earliest starting time may be XD also, XD plus 2 minus YE. Okay. So, now I have written for all the activities the equations which connects the earliest finishing time and the how much days the crashing can be done for each activities. Continuing with the forward pass of the PERT CPM procedure, we see that the earliest start time for activity B XA is the finishing time for activity A. Thus, the constraint corresponding to the finish time for activity B is, so XB is greater than or equal to XA. What is XA? It is the earliest starting time of activity B plus 3 minus YB. What is the 3? It is the duration of activity B. What is the YB? How many days the crashing can be done. Okay. So, this is activity B. Similarly, I have written for activity D. Finally, we consider the activity E. So, here activity E. So, what is happening here? There are two preceding activities. So, earliest start time for activity E equal to the largest the finishing time of activity B and D, this B and D, because the finish time for both activities B and D will be determined by the crashing procedure. We must write two constraints for activity E, one based on the finishing time for activity B, another one based on the finish time for activity D, that I have explained previously. So, when you simplify, this will be XE plus YE minus XB greater than or equal to 2, XE plus YE minus XD is greater than or equal to 2. Recall that the current production level made completing the maintenance project within 10 days. Thus, the constraint for finish time for activity E, XE, should be less than or equal to 10. This constraint need to be added. In addition, we must add the following 5 constraints corresponding to maximum allowable crashing time for each activity. For example, activity A from the table from the previous slides, we have seen maximum 3 days can be crashed. So, the value of YA cannot exceed 3. So, it should be less than 3. So, YB, number of days activity B can be crash days, less than or equal to 1. YC less than or equal to 2. YD less than or equal to 2. YE less than or equal to 1. As with all linear programs, we add the usual non-negativity requirements for the decision variables. Now, we have to formulate the objective function, because the total project cost for a normal completion time is fixed. How much? It is $1,700. We can minimize the total project cost, that is normal cost plus crashing cost, by minimizing the total crashing cost. So, the linear programming objective function becomes 100 YA. How we got this 100? You see this? If you reduce this duration for activity A by 1 day, the cost will be 100. So, how many days we have to reduce YA, okay, and YB, YC, YD and YE. So, the objective function is minimizing the total crashing cost. So, now I brought the complete linear programming models. So, here the first one is objective function, and there is constraints for all activities, and this constraint XE less than or equal to 10, it is the constraint provided by the management. The last YA, YB, YC, YD, YE is the maximum allowable crashing times for each activity. Now, this problem I am going to solve with the help of solver, then I am going to interpret the result. Now, this is the Excel model for this crashing problem. Remember this XA, XB, XC, XD, right. These variables are there in our objective, in our constraint. So, any variables which are appearing in our constraint, that need to be reflected on our objective function also. So, we have to include in our objective function XA, XB, XC, XD, where the coefficient of objective function is 0, 0, and YA, YB, YC, YD, YE, these variables are already it is there, and corresponding coefficient also given. So, if I go to N4, that is objective function, What is the objective function? As usual, the sum product multiplying the value of decision variables and coefficient of objective function. Then I have included all the constraints. So, now I am going to solve it. Data, solver. See that this problem is minimization problem, objective function is n4 and the changing cell is b5 to k5 and all the constraint I have included. This is a linear model. So, I am going to solve by linear programming models. So, when I solve it, now you see the total crashing cost is 350 rupees and YA, what is the YA equal to 1? The activity A can be reduced by 1 day and you see YE, activity E can be reduced by another 1 day. So, that means we are reducing 2 days. So, that it will become 10 days. Now, I will go to my presentation, I will interpret the result. Now, this is my final answer from the Excel. So, here the value of YA equal to 1, that is activity A can be reduced by 1 day, YE is 1, activity E can be reduced by another 1 day. So, that it will become total duration is 10 days. So, optimization software such as Excel solver provides the optimal solution for crashing activity A by 1 day and activity E by 1 day with a total crashing cost of 350. Just now I have shown this answer. So, with the minimum cost crashing solution, the activity times are like this. So, A can be crashed by 1 day because initially it was 7 days, now it is 6 days. So, activity E can be crashed by 1 day. Okay. The linear programming solution provided the revised activity times, but not the revised earliest start time, latest start time and slack informations. So, what will happen when we compress our time? The whole schedule also will change. So, the revised activity times and the usual PERT CPM procedure must be used to develop activity schedule for the projects. So, what I am saying here, that if you revised, when you compress the duration, again the whole schedule need to be found. Linear programming model for crashing, some takeaways. Note that the 2 mission maintenance project network for the crashing illustration has only one activity, activity E leading to direct to the finish node. You see that there is only one activity that is directly coming to the finishing node. So, thus we can directly write the linear programming constraint requiring the project completion in 10 days or less could be written as XE less than or equal to 10. Sometime what will happen, there will be a two activities that will end for finishing. For example, if 2 or more activities lead to directly to the finish node of a project network, a slight modification is required. What will happen, there may be one more network here, one more activity here that will end to this finish node. So, what if there are more than one node, we need a slight modification in our LP model. Okay. Now, consider the portion of the project network shown here like this. There are activity E and activity G that is directly coming to the end node, that is a finish node. So, in this case we suggest creating an additional variable xFin which indicates the finish or completion time for entire project. Okay. The fact that the project cannot be finished until both activity E and G are completed can be modeled by the 2 constraint. So, what we can do that? So, we can write a constraint like this, xFin should be greater than or equal to XE, okay, for this activity. So, for the activity G, xFin is greater than or equal to XG. So, this xFin will be provided by the management. So, the constraint that the project must be finished by time t can be added as xFin less than or equal to t. So, whenever there are 2 nodes which are directly ending to the finishing node, so these 3 equations can be added to take care. Dear students, in this lecture I have explained about time cost trade off. What is this time cost trade off? Whenever you compress the time, the cost will increase. So, we need to have the optimal reduction in number of days, so that the cost will be minimized. Then I have explained the crashing activity times. The last one, that is very important, I have explained how to use linear programming model for crashing with the help of Excel. Thank you very much, students.